Welcome to the 6th class of Interactive Mathematics or Interactive Mathematics with Mathematica. As you will recall, we started the summer pre-course with trying to convince you that basically mathematics is everywhere. It's the language in which you express ideas that has quantitative implication or has analytical dimension to it. So it doesn't matter whether or not you're actually going to heavy duty engineering or you're just trying to design a product and visualize something. Nowadays, you pretty much need element of mathematical reasoning or logic behind it. Okay. Now, I also mentioned that this class coming in, some of you have taken high school linear algebra and calculus. Some of you actually have not touched any mathematics since maybe, I don't know, 12th grade, just something very elementary from there on. Okay. So I have to make sure that you guys are on the same foothold. Okay. What I'm trying to do then is to give both the newbies, so to speak, those who actually have not even seen linear algebra or calculus, the intuitive understanding of linear algebra and calculus. For those of you who already did it, okay, for those of you who already study in high school, for those of you who already studied linear algebra and calculus in high school, hopefully this gives you a sort of like intuitive understanding of why it is you invested a year or so studying it, and you will be able to communicate that with your, I guess, less technical friends as well. Okay, and you have to do that, and you have to help each other out. Okay, fine. We talked a little bit. We started with linear algebra. Okay, the idea is you're already familiar with addition, multiplication, division, and just think of it linear algebra as trying to do it on an industrial scale. So instead of doing multiplying one number, just multiplying a whole bunch of numbers simultaneously, so to speak. Okay, and that's when you start to. I started to introduce the concept of vector as column of numbers, so you can process them simultaneously. And linear algebra is everywhere, but at the very least, the most relatable concept you should have in your mind is to think of simultaneous equation, right? You have two equations in two unknown. That's something you kind of did when you were in grade school. Three equations in three unknown. Well, with mathematical algorithm, you can do 1,000 equation in 1,000 unknown. Okay. And then we talked about condition in which that exactly is not it's not guaranteed, right? When you talk about two equation and two unknown, when you were in grade school, you were guaranteed to find a solution, unique solution, one solution, right? For x1 and x2. Well, in real life, it turns out that you actually have three situations in life. You can have unique solution, which is a case of, three equation and three unknown, two equation and two unknown in your grade school, or you can have infinitely many solutions, because some of the equations are actually just multiples of or combination of other equations. Okay, so in which case you're actually not getting independent information that crosshair your solution. So you get infinitely many solutions. On the other hand, you can also get no solution. This is where the left-hand side coefficient are the same, but the right-hand side is not. So you get something like a parallel line. Okay, well, that parallel line can happen in any dimension. So a lot of matrix algebra focus on, multiplying square matrix with a vector of dimension n. Okay, so n by n matrix multiplied by vector of dimension n, and you get output y is also a vector of dimension n. Okay, and then there's a lot of theory about, how can you find out whether or not this matrix will actually get you unique solution, infinitely many solution, or no solution whatsoever. Okay, and so that's in the matrix theory study. Okay, all you need to know is that in life, chances are basic linear operation is part of life, and you might need to do it, and you will need to do it in multiple, in more than just one variable. Okay, so you have 10 variables or something like that. Okay, Very good. So that's a basis of linear algebra. Now I pivot to calculus. Calculus also can do things on an industrial strength. It can also do things to multiple variables at once. But for this class, I'm just going to focus on one variable, okay? Because I'm introducing some more powerful machinery. This machinery, I'm going to be demonstrating on univariate calculus. In other words, y is a function of x, okay? And why do we need to know that? Okay, and so let's go to some class notes. Okay. Right. So let's summarize again the motivation and think of this as a way of communicating. Okay. Think of division. Okay. Think of division. If your equation is y is equal to mx plus b, again we go to just one variable. So m is not a matrix, x is not a vector, but this is just a single number, right? You did this in grade school, right? You did this in grade school. So if y is equal to mx plus b, okay, how can you find out what m is? Okay, so what you do is you basically move x a little bit, you move y a little bit, you can move it as big as you want, right? So m is the difference in y divided by the difference in x, right? So if your equation is distance is equal to speed times time plus some kind of starting point, right? How do you find the speed? Well, you take the distance at a moment in time, subtract it from another distance at maybe earlier moment, and divide by the difference in time. Okay, that's it. That's what you did. Likewise, if your equation is revenue, revenue is price times number of items sold, right? Plus maybe you had some earlier accumulated revenue. How do you find the price? Well, you could do it by just taking the revenue divided by number of items sold. Okay. Now, this has a precise meaning if all the items sold has the same price, right? But if all the items sold do not have the same price, what you get is an average price, right? So in this case, whether or not you're talking about average price, average speed, exact price, exact speed, it's the same because speed and price are constant. Yeah, that's your life, right? Simple. Now, think of multiplication. Okay, so same thing, but inverse, right? Instead of dividing a by b, you're multiplying a by b, right? If y is equal to mx plus b, or right, kx plus b, right? Basically, in order to find y, you just multiply x by the rate. Same thing. Okay, so very simple. This is something from grade school again. Well, you begin to appreciate calculus the moment you allow this to happen. So the slope or the change in y is no longer a constant. Just like, you know, you're not driving at the same speed. Okay. Or in this case, you can have something like price is a function of number of items. Now, how many of you know this? You normally think of item of something, right, as a price. It's a constant. But in economics, it's not. Well, think of oil, think of gas, right? That's called demand supply. So the higher the demand for the product, you're not just multiplying more of it, you're actually multiplying more of it at a higher price, right? Because everybody's scrambling for oil, everybody's scrambling for gasoline. So you have something like price is a function of number of items sold times the number of items sold. Okay, so now, so again, think of multiplication, right? Multiplication, same thing. Okay. Now, in division, I drew a picture. Let's try this. Let's try our little screen here. Can we go to the screen? Okay. If revenue is price times number of items sold, but the price depends on particular number of items sold. Okay. You can imagine that you can't just divide revenue by price anywhere. You have to sort of like move the item sold a little bit. In other words, take the difference between the revenue you have now and the revenue you get when you just sold one more item. So it becomes a smaller division. Okay, so let's try our little screen here. เขียนได้เลยค่ะ So I have to stop this, right? I have to stop share here. หน้าเปล่า Oh, ถ้าเขียนเลยไม่ต้องหน้าเปล่าใช่ไหม Okay, fine. So we don't have to switch. Yeah. So we can just go to a blank page, I guess, right? We can go to a blank page somewhere. Oops. Okay. Right. I'm not going to use the draw on this. Okay. We had this situation. Very simple. Very simple. Okay. You have accumulated something, and the slope of that, this divided by this, give you the speed. And we drew that last time. Okay. The point is that if you don't have a straight line, but you have something like this, so the guy speeding up, slow down, I'm still doing the same thing, except I'm going to do a tiny amount of division. Okay. So basically it's a change in Y divided by change in X, but make this thing smaller and smaller, approaches zero. That's what we did last time. That's what we did last time. Okay, so let's see if we can erase all that. Okay. Okay. Oh, okay, sorry. Okay. What I showed last time, and you saw this in demonstration in Mathematica when we expand something, right? If that function were to be y is equal to x to the power n, okay? And in this case, I'm assuming n is some kind of integer, 1, 2, 3, 4, 5, positive integer. The point is, how do I get change of y? Change of y is equal to, right, f at x plus change of x minus f of x, right? So I divide this by change of x, divide this by change of x, and I try to make this guy go to zero. Okay, I did not prove to you in general case. And in fact, you know, for general case, there's been like a proof for many hundreds of years. Okay, I just show you, okay, I just show you special case where this is x plus delta x to the power n minus delta x divided by to the n divided by delta x. Okay, and all I did was to say that you guys remember this rule, a plus b square, right? It's aa plus ab plus ba plus bb. Now, if you did this 3 times, you're going to get 3 a's. Well, if you did this n time, just as over here, you're always going to get x to the n, which, sorry, I have to erase this. How do I erase this? Erase this. Ah, okay. sorry, my bad. Okay. You're going to get the first term, which is this, but you subtract it away, it's going to go away. You're going to have n x to the n minus 1 and then delta x. Well, and then you're going to have something else with delta x square, blah, blah, blah. The point is you have this delta x on the bottom. So this thing cancel each other out, but it hasn't canceled enough. So everything to the right here is going to have delta x somewhere, but this term doesn't have it. So that's how you derive the derivative. Okay, so if function is x to the n, if f of x equal to x to the n, okay, now let me write this all out so that you get used to both notation. Derivative, they call it dy dx or f prime of x is equal to n x to the n minus 1, right? That is simply the consequence of what we did before. So you saw this. This is no magic, okay? This is no magic. Now, what I'm telling you is that this is how calculus proceed. This is the building block, okay? Next thing, you have to believe me that this works for any kind of n. So it could be something like x to the 1.2. Derivative of that is going to be equal to 1.2 x to the 0.2, something like that, okay? Or x equal to the minus 7, okay? Derivative of that's going to be minus 7 x to the minus 8, okay? So this rule holds. Right. So let's go to log. The way calculus proceed, and this is, you know, you don't have to actually read book in calculus, but this is exactly what calculus did. Once you got this, okay, so this is a simple formula you start with, right? This is what you start with, okay? This is called binomial theorem. By the way, just for fun, I want to show you that this is actually the coefficient. If you take something like a plus b to the power 8, okay, you're going to get a to the power 8, right? Plus this, 8, a to the 7b, plus 28, a to the 6b square, okay? This is because, I don't know if you ever play this game where you take a coin and go to the right and left, okay? So this is how you actually add the combination front, back, back, front, back, front, front, back, back, front, front, back, sort of thing, okay? Anyway, that is just a little fun thing. It's called binomial function, okay? So this thing, I can, right. Now, what happened is, okay, you have to, well, for now, take my word for it, that it works for any real number n, but I'm not going to show it here, okay? So the proof is not so simple. Moreover, if it's not x equal to n, but x is some other function, exponential e to the x. Now, you some of you who have not, you know, done mathematics in high school may not have seen this, but exponential and logarithmic is another function that you are going to be using. It's one of those things where it's fundamental in life. That's how you make money grow when you put it in the bank, for example. Okay. And then you have function like trigonometric, sine and cosine. Now, to be honest with you, sine and cosine will not happen, will not come out to your life much if you're not in engineering. Okay. But if you involve any kind of mechanical system, or any kind of shape, any kind of structural engineering, any kind of geometric, obviously, calculation, these are going to come up. But okay. The point is that these are basic functions. So mathematician, so let's say Newton. Okay. By the way, not just Isaac Newton, but another guy called Leibniz. And there's kind of like historical argument as to who came with calculus and so forth. And incidentally, the notation we use is not it's not Newton's notation. It's notation of Leibniz. Leibniz is German. Newton is English. Okay. There's a good story why, you know, they have this kind of like intellectual combat between the two. It's kind of fun. Anyway, so if you can find the slope of x to the n, you can find the slope of e to the x, you can find the slope of log of x, you can find the slope of sine of x, of cosine of x. That means that if any of these functions shows up in whatever your profit function, your calculation of building dimension, I don't care what it is, you can always find the rate of change. Okay. And technologically, that's the most important thing when you go forward. Well, in calculus book, they will proceed invariably just like this. If you have two basic functions and you have a more complicated function that created from adding them together, well, the slope of the combination of function is the combination of the slope of the function. And that makes sense, right? If you have one source of profit and you have another source of profit and you have one source of revenue, another source of revenue, and your total revenue is a sum of two sources, right? how does your revenue grow with amount of things you sell? In other words, what's your price? That's the derivative, right? Well, one source of revenue gives you one price. Another source of revenue gives you another price as a function of units, let's say. Okay, you add them together, right? So it's kind of like rate of change added up or subtract, okay? And then you have this thing called multiplication rule or product rule. What if you have two functions? What if you have function of function? So these are things that, again, once you have the intuition, okay, all I want you to see is the fact that we have basic function, x to the n. We have this thing, this thing, this thing, and this thing. And for each of those, there's a formula for calculating the derivative. And if the function is created by putting them together, then there are rules, okay? So apply the basic rule, okay? So these are the rules, and you will learn this in your, first year mathematics. I think in detail a little bit, you need to do that. Chain rule and so forth. By the way, I mentioned chain rule in connection with Ito's lemma, that is the foundation for the Nobel Prize winning formula for option price. But this is kind of like a traditional version of chain rule. Ito's lemma is like a fancy version of this. Okay, but I digress. Right. So just as you think of multiplication as the inverse of division, you can also think of here, right? Integration is kind of like a mathematical inverse of differentiation. Now, I'm going to wave my hand right now for the interest of time, just to say that, well, just as if you have x to the power n, and you take derivative, you get n, x to the n minus 1, right? It's a process. X to the n on the left hand, you do something to it, you get n x to the n minus 1. How do you go the other way? Well, if you have a to the b, to go the other way, what do? A to the b minus 1 divided by b minus 1, right? Because this is kind of an inverse function of the other. Well, think of this. Think of integration as the opposite or inverse of your differentiation. Okay, so watch this. Watch this. Okay, now you have this function. Watch this. Right? How do you go from here to there? You take the slope. Okay, that's like dividing, right? Dividing this by this, you get that. How do you get from here to here? You multiply, right? So for this block, you get here. From this block, you get here. So you multiply. So this is kind of division. This is multiplication, right? Now, the fancier version of this is what? Well, the fancier version of this is, instead of taking the slope at any point, I'm going to take slope at this tiny point. Okay, same here. Instead of multiplying area width times height, I'm going to take small width times small height. Small width times small height. Small width times small height, and add them up. Okay. And because you're actually adding them together, you get the same word, integration. So that's why if you want to find the area under this, right? You used to be just multiplying this by that, right? Okay, so you take the slope, this divided by this gives you that. This multiplied by this gives you that. Right? From the left to the right, you know how to do this. Well, calculus asks you to do the same thing. So I get the slope here. If I want to multiply, instead of multiplying like this, I can't do this because the function is changing. So I multiply a little strip at a time. And this going back and forth is known as fundamental theorem of calculus. Now, you don't need to know, again, I'm trying to give you the intuition side. So, okay, think of, okay, just as multiplication is the inverse of division, so too is integration a calculus inverse of differentiation. And that's why this formula makes sense. Okay, this formula makes sense. Now, the way it's written, okay. Okay, it's where it's written. Let me do it in Mathematica because it's much easier. You can actually do this in Word, but you have to go in a palette or something like that. Now, if I want to do this, okay, this is called integrate. Okay, so again, integrate is like adding. Again, think of speed and distance, right? If your speed varies, every microsecond you're adding distance. Okay, but you're not adding the same constant amount, you're adding variable amount. The point is from 3 o'clock to 4:30, okay, you're driving along this road at variable speed. The point is I want to keep adding infinitesimally small amount of distance, and that's the mathematical word of integration. Okay, so differentiation is finding infinitesimally small or instantaneous slope, tangent slope, a very tiny change in y divided by tiny change in x. Okay, if I want total change in y, I just multiply y by x, but I can't multiply the whole shebang, right? I have to multiply by a little tiny bit. Now, if you knew the average, you can do that. But what I'm trying to say is that integration is like trying to find the total distance you travel from the beginning of the hour to whatever, the end of the afternoon, not using average speed. Okay, think of it that way, right? Let me say that again. From 3 o'clock in the afternoon to 4:30 in the afternoon, you're looking at your car speedometer. And every microsecond, you write down how fast you're going. Look at the speedometer. Speedometer sometimes say 50 miles an hour, sometimes 58, 51, 52, 53. You just multiply whatever by a microsecond, and you keep it in the logbook, and you wait another microsecond, right? And you multiply microsecond by the speed at the next microsecond, you add it. So this is how you integrate the whole distance you travel. Okay, so the most basic things in life you can do besides addition and subtraction is multiplication and division, right? Likewise, calculus is the most fundamental things in life, because what you're doing is multiplication, I call it integration, and division, I call it differentiation. Okay, except do it in a very instantaneous way. Okay, so the way it's written, unfortunately, there's some reason why this is actually the most concise notation. Okay, integrate. Let's say I have f of x. F is the speed. Let's say I can do that. Speed, time. Okay, and time going from A to B. Okay, that's what this means. Okay, that's what this means. I'm integrating the speed, which is a change of time, change over time, multiplied by time. So when I write this, what I want to do, I want to multiply speed by time. Okay, how much time have I got? B minus A, because I'm going from A to B. Okay, so A is 3 o'clock, B is 4:30. So B minus A is an hour and a half. Okay, so integrate means adding speed times time, a little bit of time at a time, and do this, patiently until you get from A to B. That's what this notation means. Okay, now this notation, this notation in a math book is written traditional form as this. Oops. Okay, let's have this imprint in the back of your mind. Okay, what this means is that, let's say this is my time. Okay, this is my speed. Okay, this is my speed. And my speed, let's say I start at 0, I speed up, maybe I come to a stop. I can actually even go backward, right? There's nothing wrong with that. Okay, so that. My question is, if this is a recording of my speedometer, how much have I traveled from here to here? How much have I traveled? It's obviously the area, right? It's the area. The point is, I want to add the area a little bit at a time. Okay, watch this, watch this. This is the height, right? The height is speed. What is the width? The width is change in time, a tiny change in time, right? Well, remember last class, I told you that the change in time is denoted with this Greek letter, delta. Well, this thing, as it gets smaller and smaller, becomes an English dt. And that's why you get dt. Okay? So this is kind of like very, very infinitesimal small version of delta t. Okay? Now, what is this? Well, this is the height. So this is nothing more than height times width, right? But you don't have just one width. You have so many little width, right? So this is, anybody notice that it looks like an S? Just use your imagination. It looks like an S, okay? S sum. So it's the sum of height times width, a little width at the time, going from here to here. Okay? So stare at this, right? And this can be any kind of accumulation, can be profit, can be whatever, right? That's why it's the most important thing in life. So what am I doing? I'm multiplying speed times time. Except the things that I'm multiplying with is not a constant. It changes with time. So I can't multiply one speed with the whole width of time. I have to multiply one speed for a tiny slice of time, plus another speed at another tiny slice of time, plus another speed at another slice of time, add them all up. The whole word of adding tiny strips of this at the time is called integration. And that's mathematical definition of integration. So now, even if you haven't taken a single course in high school in calculus, you must know what integration is, right? So if you have some function that generates something over time, profit, you have function, a profit function, generate profit over time. How much profit have you made from time A to time B is given by the integration. It's the area under that function, right? Because you're multiplying is an area, it's width times height. So integration is a whole bunch of width times height, but tiny width, okay? And whole bunch of them. By the way, this comes from, if you want to be technical about it, for those of you who are in high school, you wouldn't see this first. You would see what's called Riemann and sum. And you see this instead, sum, okay? And that's a Greek letter S, sigma, right? Sigma I from here to here, and then you have f of x and then delta x I, okay? So this thing, and I always like to do this, by the way. I always like to say, you know, you have something like this, f of x, okay? And as this thing gets smaller, this thing gets smaller and smaller and smaller, become d of x. And this thing gets smaller and smaller and smaller and smaller, and it looks like that. Okay, that's my story. Yes, this is the sigma, right? This is the sigma, right? So that's why the notation becomes this. It comes from the notation of summation. Okay, so once again, I want you to think of this as the sum of height times width, okay? Starting from here, ending here, but a very tiny width. So you can see why it's more precise, right? It's more precise. Now, the converse of this obviously is that if you knew how to do this, okay, if you knew the average, you wouldn't have had to do this, right? Okay, so in life, if you travel, right? If you travel and it took you an hour from here to whatever, right? And you take the total amount, you can divide it. You can take an average. That's fine after the fact. But if you're on a spaceship, you can't do that and then, you know, wait for the whole trip because you can't calculate the trip. In order to calculate the trajectory, you have to do it instantaneously. You can't say, oh, what's my speed? When am I going to get there? Well, I'll just get there and I'll take division. You can't because you're right here. You're right here. Okay. So that's why in order to calculate any kind of trajectory, any kind of analysis, you need calculus. Okay. Even though, you know, at the end of the day, you can say, well, how far was the space? How far was the space orbiter? Well, how far did it go and how long did it take? You can do that. But as you are controlling the spacecraft, you cannot do that. You can't do the average thing, okay? So that's basically, if I want to give you this, the first thing is, this is the power of calculus. The first power of calculus is precision. Okay, it's precision. It's precision. Now, let me give you another example. Let me give you an example. Let's say I want to mold this thing. You see in my hand? See this thing in my hand, right? And so I have to calculate how much of plastic do I need for this thing. Okay. Now, if I didn't have calculus, can I calculate the amount of plastic I need? Well, if what I have is a blunt object like a block or a cylinder, I can do that, right? But I cannot do it for this shape. Okay, because this is not look at it this way. This is not a Coke can, right? It has a curve. It has a curve. So how do I calculate the volume of this? I integrate, right? Just as you can add height and width, tiny slice at a time, I can add what? A little this, right? This is the, look at this way. From your point of view, this is a this, right? So how much volume do I need? How much plastic do I need to make this thing? It's a little this. One this big, one this small, right? But the shape of the this changes. So what I'm gonna, I just broke the disc. So what am I going to do? I'm going to take the diameter of the disc, right? But the width of that disc is going to be a tiny slice at a time. So I'm going to integrate from here to here. I'm adding all the volume of the little disc. So I can do that. So everything in life, even though, you know, I told you that it comes from dynamics, from moving things over time. Everything you do, okay, you're doing product design, okay, you're going to do this. By the way, and this is a bit of, well, not a sidetrack, but we have a lab, right? We have a 3D printing lab. That lab is going to allow you to draw a picture of things and make like a little bunny or something like that and send it to a printer. It's going to print 3D. Now, what Mathematica does is when you enter the geometry of the rabbit in it, it's actually going to minimize because you don't want to use the plastic for the whole thing. Let's say you just want to have the outside shape of the plastic, right? How can you minimize amount of plastic used? That's a mathematical problem. Okay, so you can use Mathematica to program the shape of a bunny, program minimization so that you want to use the minimal amount of plastic. So it's lightest, it uses the least amount of material. And then use Mathematica to do that optimization. I'll talk about it later. And then you send it to a 3D printer. Okay. If you didn't have the mathematics and you just have a CAD program, let's say you have a SketchUp, okay, you would actually be using a lot of material. You'd be wasting a lot of plastic. okay? Because you have to minimize it by hand, right? But with Mathematica, you can actually do the optimization. So the cost of your rabbit doll is going to be much less than cost of your friend's rabbit doll who doesn't have calculus at his or her disposal. Okay, so this is, so don't think that it's far away. Okay, well, anyway, the first thing I told you is that the power of calculus is precision. Okay, so you're not multiplying average. You're not multiplying height by width. You're multiplying by instantaneous height by instantaneous width and adding them up, for example. So you get precision. That's the power of calculus. Second thing you get is the ability to model. Okay. Now, I'm going to give you a thought exercise. Do you guys know what modeling is? Now, this is probably more valuable than all the interactive math I teach you, actually. Is what do you mean by modeling? Anybody? Well, if you think about catwalk model, right? Why do you have a catwalk model? Because you don't know what the clothes would look like on a real person. So you just put it on somebody and hopefully give you an idea, right? That's probably not realistic because you don't look anything like the model, right? So when you wear the thing, you're not going to look like someone on a catwalk. But anyway, that's beside the point. The idea of a model is that it's not reality. It's not reality. It's an abstraction. At some level, involves some kind of abstraction. At some level, it involves some kind of abstract representation of something you're interested in. Okay? Now, in the context that I'm talking, and this is where modeling becomes the key part of your BASI curriculum. A model is how you can derive any conclusion about something given information about something else. Okay, let me say that again. Okay, let me say that again. A model enables you to derive some conclusion about something given information about something else. Okay, now in the catwalk model, that's not a very good example, but you know, what you get is what? Information about what the clothes would look like. Okay, given information about what you can see on the model. Yeah, that's not really the sense that we're looking for. What the sense I'm looking for is this. If you knew X, you can make some conclusion about something else, and that's why. So when I'm talking about modeling, okay, I am talking about mathematical modeling. Okay, whether or not this involves high power calculus, linear algebra, or some kind of Excel lookup table, I don't care. Okay, this is not about how complicated it is. This is about notion. So think, use your head, use your, I guess, intelligence to imagine. This is exactly what mathematical modeling is. It's relating something to something else. Okay, you only know about Y. So if you want to know about Y, right? If you want to know about Y, everybody wants to know about Y. Okay, for example, Y is the number of the lottery, right? Are you ever going to beat any competition? No, because when the Y is given, everybody knows what the Y is, right? But what's the point? You cannot buy lottery ticket after the number has been announced, right? Right? So when Y is known, you can't do anything special, right? It's just an information. It's just okay. Let me tell you this. Yesterday's lottery number is 39145. Does it excite anybody here? No, because you know what that Y is, and so does everybody. Okay, how would you make money? You would make money if before anybody else in the world knew what Y is, you know what the Y is. Okay? Now, how would you know what the Y is? Let's say that X, okay, is some weird deformities like a dog with 3 heads or something like that, right? That happens in the news. What do people do? They try to reach into a dog with 3 heads and come up with some number that would be the lottery winner, right? That's their model. Okay, that's the model. Of course, it's all silly nonsense. It doesn't predict anything. It's completely stupid, but that's exactly what a model is. So I am telling you that regardless of your level of sophistication, a human being reasons by modeling. Okay, let me say that again. Okay, you can be intelligent or you can be stupid, but as a human being, the way you reason is by modeling reality, because you always have to make some kind of anticipation, prediction. Okay. In fact, let me give you another instance. Let's say there's a projectile. Okay. Somebody is throwing a ball from over there. Okay. That's your X. You know that ball. What is your function? What's your model? Your model is your understanding of how the ball trajectory works. And that tells you that in 2 seconds, in half a second, that ball is coming to your head, right? So Y is the position of the ball in half a second. X is the position of the ball right now. What is your model? Your model tells you where the ball is going to be in half a second. It turns out that in half a second, that ball is going to be directly on your forehead. So what do? You duck, of course, right? Presumably, okay? Every single activity, every mental activity that you do is modeling, okay? Likewise, what if X is the state of your market, number of clients, okay? People who are using this app, people who are in e-commerce, blah, 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 right? What do you want to model? You want to model their behavior tomorrow, because whatever they bought, you can't sell them. You can only sell things that they haven't bought, right? Okay. So the model is their demand function. How much of this thing they're willing to pay for if you make it, right? And if your model say they're willing to pay 5 baht for this, but your other model say it's going to take you 7 baht to make it, what's your decision? Right? And that's how you win or lose. You win by coming up with better model. Okay. So as a human being, okay, as a puppy, you know, your success in life is being cute. Okay. As a professional worker, people who are doing, you know, not manual job, thinking job. Okay. Your ability to succeed comes down to this. Do you have better model than the guy next to whatever? Okay. If you have a better model, you win. That's end of the story. Okay. Now, let me backtrack from that and just give you a more discrete version of what calculus does. Calculus allows you to make model. That's it. So all the decision making based on science, whether or not it's physical science, chemical science, biological science, economical science, social science. Okay, I'm talking science in this case, like not a physical science or not. So psychology is a science, right? That is also based on a model. So the way calculus makes a model is to do this. It's actually relating Y. Okay, so I told you already, right? Y is a function of X. Okay, y is a function of x. Let me tell you this. Let me just write this down. Y is a function x. Again, what's x? X is something you know, your competitor know, everybody knows. What's y? Y depends on f. Your job in life is to come up with better f. That's it. That's it. Except in calculus, the way you model, once you get this is kind of like this end result, right? In calculus, instead of having this, sometimes you have information about f of x, sometimes you have information about f derivative. Oops. F derivative x, right? The point is that the way calculus model things is relating something like this. For example, x, something like this, x, say, equation. Okay. You want to know what y equal to f of x is, right? But information doesn't come like that. Information comes from observing nature. So how do you model nature? You happen to notice something like this. X is equal to 5 of dy dx, or f prime of x. Okay. Minus 7. Okay. Okay. Plus 8 f of x. Okay. So somehow this is an equation. This is an equation. Cappuccino. Okay. You're not giving y as a function of x, but you have relationship. You notice that f of x, f prime of x, and x are related in some way. And this is called differential equation. The reason it's called differential equation was because, first of all, it's equation, right? A is equal to B is an equation, but equation is stated not in terms of y equal to f of x, but in terms of derivative. So the derivative is giving you more information. In other words, I'm not telling you that this is how you learn. I'm saying the speed that you learn is equal to 5 times how much you already learned. So if learning is a function over time, the speed is the derivative of your learning over time. I'm telling you that you learn faster if you already had prior knowledge or something like that. Okay, that's how I make statement. So in life, a lot of modeling is not relating A to B, but it's relating A to rate of change of A. And that's very important. Okay, let me say that again. Let me say that again. Okay, you have this kind of modeling where you're trying to relate A with B. That would be like statistical modeling. Okay, likelihood of being able to sell this product with whether or not your client is a boy or a girl. So you're relating A and B. A lot of time you're relating some quantity with its own rate of change. Okay, and that modeling can only be done when you can express the rate of change, which is calculus, in particular derivative. If you express it in equation, it's called differential equation. Okay, so calculus, you know, if I give you y is equal to function of x and I ask you to calculate derivative, that's called differentiation. If I have a function like a speed and I want to find the accumulated change over time, that's called integration. That is going to give you all the precision in modern world. I told you that already. But the next step, the next power of calculus is not just that. It's not calculating slope. It's not calculating integration. It's relating something with its own rate of change. Yep. ใช่ครับ ใช่ครับ So sometimes you would see something like this. dy dx. This thing is going to give a, sorry, let me just use, yeah. So it's going to give you something like this. dy dx is equal to ax, something like that, right? So x is the underlying quantity, like time. Y is some attribute, something you are trying to model, something that changes with time. So maybe that would be like a distance, right? The point is you have x and you have this, which is f, right? And then you can say something like y. So there's x, there's y, there's a change of x, change of y, all kind of stuff. It's all mangled in here, okay? The reason you can do better than your friend is because everybody looks at this. But with the power of calculus, then you can make prediction y is equal to f of x. Because, you know, it's implicit in here, right? It's implicit in here. So it's not, so let me think of it. Let me just say this, okay? Again, trust me, okay? And I even challenge you. Anything you do in life that has to do with analysis is about coming up with a model. It's about given an x, create an f that gives you y. In your statistical world, you try to find y as some kind of coefficient multiplied by x, x being a factor. So that's one way of building a model. It's sort of like statistical modeling. Another way called dynamical modeling is you notice that y somehow is related to its own behavior, like y is related to its speed. And this is the original meaning because what? Because the reason Newton invented calculus was because he wanted to relate it where an apple is with where it's going to be given the rate of change. In fact, he's more interested than rate of change of apple over time. He's more interested in that because he's looking at what's called second derivative, which is an acceleration. Okay, so far I've only talked to you about car driving at a constant speed, right? So if it changes, well, that change in speed divided by time becomes acceleration. So you have position. Position divided by time is speed. Change in speed becomes acceleration. All of this has to do with two things: position over time. Position over time. Position itself, time itself, position over time, speed, change in speed, acceleration. So Newton wants to have, well, he came up with the physics equation that relate where the apple is to where it starts, the initial velocity that it's falling, and the acceleration due to Earth's gravity. Once he's done that, then he solved for how the gravity works. Let's put it that way, okay? The point is that he needed calculus because he doesn't have apple and orange. He only has apple and time. He has apple, time, position of apple, okay? Apple now traveling at this speed, apple later due to acceleration of apple. So he's not describing apple in terms of orange, which he would have to do with, if he were to do that, he would have to do something like probabilistic reasoning, right? Okay, the chance of seeing an apple given that you see an orange because it's a farm or something like that, okay? He's only interested in apple and time, except he has information about how apple, where it is, relates to how fast it's going, how fast it's accelerating. Bracket, parenthetically, accelerating because of Earth, okay? But that is the physics part. That's the physics part. But the calculus part is this. And he came up with the Newtonian gravity equation, okay? Now, you are not trying to come up with the gravity equation of gravity because you're not trying to discover basic science. You're trying to come up with some function that maybe allows you to predict how much you're able to sell this thing that you design. Okay, like demand function. Okay, so your is a little bit, it's not so universal, right? Okay, so you're not trying to find the equation of gravity that applies on Earth, Moon, Sun, and star. You're trying to find an equation that relates certain parameter about your design. How much you use the quantity of plastic, blah, 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 the design, this and that, the number of people, blah, 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 with your profit. Okay, so that's the power of calculus. Now, let me take a break because it's, I got to say, okay, so take 3-4 minutes break and we'll come back. What I want you to understand is the relationship between differentiation and integration, right? It's nothing more than the relationship between taking the slope, okay, dividing y by x, and multiplication, adding height by width, right? That's what I want you to understand. Having said that, the mechanic of doing it can be very difficult. And so that's why you have tools like this. So this is something that, you know, Python cannot do, but Mathematica can because it understands the symbolic logic. So for example, let's say I give you something like this, right? Say something like this. Okay, watch this. Now this doesn't, it's something that, you know, it's kind of weird. You've never seen it before. You don't know what it is. I haven't seen it before. It will probably take me days, you know, to come up with the integration of this. But so you can use this function, right? So this is kind of integrate. Now, if I did this, I haven't specified that I'm trying to find the distance, sorry, the area under the curve from A to B. Okay, I'm just giving a formula, just a regular formula. So instead of putting x from A to B, I just put in x. Now, how would you use it? Well, if I want to go from A to B, I just plug in A and plug in B and take the difference. As simple as that, right? So this, by the way, is called indefinite integral. Okay, so in normal traditional form, it would look like this. Okay, oops. Yeah, so this here, right? This is a traditional form, and we did this already. Okay, now if I didn't put in A and B as a definite, this is called definite integral because I define definitely I want to go from A to B. If I want to go any kind of formula, it's going to give you something like this. So this is going to be a notation. It doesn't have A, it doesn't have B. This is known as indefinite integral. Okay, just some words. So when you see it in a basic math class, it's nothing. Now, I showed you earlier, right? This integration is an inverse. So if I start out with x to the power 3 divided by 3, I take the derivative of that. I take 3 down, cancel with the 3, and I get 2. So x to the power 2. Well, so this is how I want to demonstrate that. Integration is the opposite of differentiation. So if I integrate x squared, I get this. If I if I differentiate, do I get this? Same thing, right? So integration and differentiation is kind of the inverse of each other. That's basically what underlines the fundamental theorem of calculus. So I don't care what it is. If I take the derivative of this, okay, and then I integrate it, what should I get? What do you think? What do you think we should get? Original f of x, right? Right? So inverse, I can write it in the opposite way. I can put integrate here. Okay, so that underlines my message earlier. It's an inverse of one another, right? It's okay, fine. And this is so if I want it in indefinite case, let's do this. This is the most indefinite case for the x to the power n. Oops. Right? I get this, see? So because derivative of this will get you that. Integration of that will get you this. So that's the formula why it's x to the power n plus 1 divided by n plus 1. Okay. Right. So this is very generic. So if I put in 5, get that. Now I told you before, right? It works for decimal number as well. So let's see that. Minus 1.234. Right? So that's equal to x to the minus 2. Right? Oops. Yeah. Sorry. Yeah. X minus plus 1 minus 1. Oh, this is already minus 1. Okay. So it's minus this and then 2. So let me do a few things at a time. Okay. Right. So it's minus. Oh, I was trying to do this first. This is what I meant. Okay. So if this is differentiation, right? And you happen to see this, you can guess that integration right? Okay. Integrate this, we'll get you this. Okay. Why? Because this is x to the minus 4, right? So minus 4 minus 1 becomes minus 3. So that's this thing, right? And then this 3 and 3 cancel out. Okay. So that's just to tell you that with this tool, you can't find any of this in Python, because Python doesn't do analytical. It only does this. With Python, you can do this. You can do this. You can put in number, say 3 and 4. Okay. Python will give you this. Actually, it will give you this. Okay. Python. But if you want to do something like find out the relationship, it doesn't. It doesn't. Okay. So again, x to the n being any number, this is indefinite. Now, if I want to plug in between 3 and 4, that's the same thing as 4 over here minus. Okay. So if I want to do this between A and B, what do you think is going to happen? It's going to replace this expression with B and A and take the difference, right? So watch. See? B and A and take the difference. Okay? Basically, what it means is this. This happened. Okay? Right? Simple as that. Okay, fine. So this is the integration of this, evaluate at B at the right, minus by the left. Okay, so we know how to do that. The point is that I can do it with very complicated function. If I ask you to take the derivative of this function, it would take you minutes, maybe 10 minutes to come up with this. Okay, but I can guarantee you that if I give you this and I ask you to integrate, you would not find it. Okay, I would not find it, but with the tools, it does. Okay, so it's a very clever analytical tool. So this allows you to sort of like put in anything. So any kind of function. So you can think of any kind of relationship that you want to create as part of your invention or innovation. Okay, it can be, you know, in health science or whatever. I don't care. Okay, now I want to show you this. By the way, this is something that, again, I would be building into my interactive notebook. But in this case, because simple elementary calculus is so ubiquitous, it's already, you know, somebody already did this in Mathematica. This is exactly what I was talking about. Okay, I want to know, let's say this blue line is my speed. This is my time. I start at 0 speed. I multiply by time. I can't multiply the whole thing by an average because at the starting point, I don't know what it is, right? I want to do it instantaneously. So how do I do that? I take the height times the width, except the width is what? It's kind of big, right? It's kind of crude. So is this going to give you the area under the curve from here to here? It's going to get something actually close. So look at this. The actual number is 5.7506. by taking slice this big, you get 5.7591. Okay, so you're off by a little bit. Now, what if I did this? I make the slice smaller and smaller and smaller and smaller and smaller and smaller. See, it's accurate up to 4th decimal. Okay, let me try again. Okay, see, it's far off, right? So you can see that 57558. That's pretty big. That's a very crude approximation. That's like saying in 5 hours, I take my average speed on the 1st hour, the 2nd hour, 3rd hour, and 4th hour, and add them up, right? Now, what I wanted, so this is my big delta X. So it's too big, it's too crude. So make it more fine tail, and the approximation gets better and better. Okay. As this gets to be infinitesimally small, okay, that's when you get integration. Okay. So once again, you are summing height and width, but you're making the width smaller, so you have more strips to add. Keep adding. Okay, so that's what it does. So that's integration. That's integration. Now let's go back to my note. What does, oops, yeah. My notes gives you this, okay? So before the break, we got this thing. Precision, again, because you can multiply and divide things, but the things that you're multiplying with is not a constant. It's not an average. You're not getting an average speed multiplied by time. You get instantaneous speed multiplied by instantaneous change in time. You get modeling, because sometimes, and the first example of this is, of course, the reason for calculus to begin with, relating object with itself, but a position with its velocity and so forth. Okay. By the way, that's how the best mathematician in calculus, one of the best mathematicians in calculus, actually were the French. You know why? You know why? Because a little bit after calculus was invented, I don't have the timeline exactly, but you know Napoleon, right? Anybody knows? Yeah, Napoleon was very big on invading friends and neighbors, right? Well, back then, what did Napoleon use? He used cannon. Okay, the reason the French artillery was very developed was because Napoleon liked to shoot cannons. Okay, and how do you shoot cannon? Well, you put it at an angle, right? And how is the trajectory? How can Napoleon tell his troop to fire a cannon that would land exactly? Well, it wouldn't be kilometers, right? Back then, maybe let's say, my guess is 1.7 kilometers. Okay, that's pretty good. That's pretty far already. But let's be realistic. Let's say 800 yards. Okay, I want this ball, this weighs 20 pounds, round metallic ball, to land in the direction. I know the direction, so I can just aim it, but I want it to land exactly 840 yards. Okay, and I know this because I'm actually trying to invade a castle. Okay, and I know the distance from here to there is 840 yards. So I don't want it beyond that. That's beyond the castle, or in front of that. That's just peasant farming or something. I want to bombard the castle. I want exactly 840 yards. How will I know it? Well, based on propellant, I can tell you what the initial speed of the musket, of the cannonball is, right? I put this angle, that's calculus, sine, cosine, yeah? I know from Newton that I have acceleration downward. Once you fire a cannon, only acceleration comes from Earth, right? Because the first acceleration is from the propellant, from the explosion. But once it leaves the muzzle, leaves the tip of the front of the cannon, it gets a finite speed, okay? And that speed, if you're shooting it up, it's just going to slow down. Okay, it's just going to slow down. It's going to slow down because it's being accelerated downward by gravity. Now, how much time he has, that's how it depends on the initial speed versus the Earth gravity. Well, how much time he has, if he has the horizontal velocity, that's how far it would go. right? So this thing gives you how much time it has, but because it has this horizontal component, that's how much time it would go, because by the time it comes here, it hits the ground. Okay, it can't go any further. That's it. That's how Napoleon calculated trajectory of his cannon. Okay, now because the French artillery very good with calculus, Napoleon was very good with cannons. Basically, that's end of story. Okay, so that's why, you know, even today, by the way, you still use calculus. Okay, when you fire like howitzer, you know about the war in Ukraine, M777, right? It uses a rocket about 155 millimeters across. That is still governed by Newtonian physics. Okay. Now, smart bomb does something else. It has fin, it can fly a little bit, it can extend the range, but that's you know, you use computer for that. Okay. But artillery fire is still Newton, nothing more than, or Newton Leibniz. Anyway, so it's using this, you know, kind of thing. Right, fine. So let me show you how that's done. Well, I'll give you, this is not, you may not understand what this does, but let's say in a lot of modeling, you try to find exactly when the function hits 0. Okay, now this is a general form of a function, of an approach. It's a mathematical puzzle, so to speak. The puzzle is to say, I have a function, tell me when that function is equal to 0. Now, the intelligence is for you to look at a business problem, economic problem, spread of COVID, this, that, blah, 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 in terms of equation. And that equation, once you've done all the simplification work, once you've done all the reasoning, it comes down to some kind of puzzle that you need to solve. Well, one form of that is finding 0. Okay. How would you find 0? If you knew a function, now here's the thing. Okay. Now, I want you to think of this in your head, right? Let me go over there. Obviously, I asked you this question. Okay. Where does the function hit 0? You know, it's right here, right? It's red dot, right? Now I take away your senses. Okay? And I land you over here at the green spot. Okay? Imagine that this here is like a valley. Okay? So this is like a mountain, right? This is a mountain. Okay? And goes down. And this is, let's say, a sea level. Okay? I asked you, where does the land end? Now, if you are actually, you know, looking back from a drone or something, let's say you have this 2-dimensional Earth, okay? It's actually 3-dimensional. You know exactly that this is where the land ends, right? Now, I ask you the same question, except I don't tell you this. I tell you what the shape is, but you can't see it. You can only see here, right? You can only see here. You're standing here on the top of this mountain. The idea is that in order to estimate where that red point is, you just do the slope. Okay, so I'm standing over here. Okay, I'm standing over here. Let's say I am 100 feet above sea level. So I know I'm 100 feet above sea level. I also know that the mountain I'm standing on, okay, has instantaneous slope of 10. In other words, you go one foot here, you go 10 foot, right? That's the gradient of the mountain. You can do that, okay? So again, you're standing here. You don't see anything, right? You know where you're standing. You're standing 100 feet above seawater. You know that the mountain is going at a 1 to 10 rate. What is your guess of where the land's end? Well, 10 feet. Yeah. Well, algorithmically, you would be doing this, asking the computer to do this. Now, this is called Newton's method. What happened is that the first approximation is wrong. Okay. Then you get back to the mountain. You do it again. This is called Newton's method. Okay. You will not be doing this yourself. Computer will be doing it. But you have to understand that your problem in life has a mathematical counterpart. And this is something I cannot stress you enough. You are not human calculator. You are not a human calculator. Okay? Your job is to understand the problem you have and the mathematical analogy. Translate your problem into mathematical analogy. Let's say that mathematical analogy needs you to find 0. Then you send it to Mathematica and some kind of algorithm. Now this thing, Python probably does very well as well, MATLAB and whatnot. Okay, but that's what it's doing. How is it doing? It's evaluating the slope. And then take the first shot, take the second shot, eventually you go. Okay, so this is called Newton's method. Okay, there are situations in life where once you have analyzed your problem, you outline everything you know, you play with it like a Rubik's Cube, you simplify it as much as you can. You end up with some equation and you want to say, when does this hit 0? That's what this means. That's what this means. Okay. Okay. So now this, okay, I talked about precision modeling finally, and this is the most relevant part of Basai education. Math calculus gives you ability to optimize stuff. Okay, what's optimization? Optimization is like maximization. Okay, maximization. Now, sometimes maximization doesn't mean that you go to the extreme. Sometimes you want to find the middle path. That's also optimal. Okay, but the most basic form is to say, I want the most. Okay, I want the most candies. Okay, I want the least pain. Okay, I want the most likes I can get. Okay, I want the least negative comments. So it's maximization, minimization. Okay, so the first thing, and this is baby calculus. The first thing is this: if this is what you want, okay, this is what you want, and this is your control, meaning you can choose. You can choose, okay? And your want look like this. How do you maximize it? In this case, your objective is not trying to find where it hits 0. You want to find the mountain's top. Well, in mathematics, this top happens because it has a flat top, right? You knew it's a mountain, first of all, okay? Now, this doesn't apply when you do this, okay? Because that's also a flat top. But let's say you knew that it's a mountain, okay? How do you know you're at the top of the world or top of the mountain? You're at the top of the mountain if you have 0 slope. So this is like solving dy dx equal to 0. Okay? So actually, this is the function that you would end up doing the Newton method just that I mentioned just now. But anyway, a lot of time you can do this analytically. You can solve for it. You don't have to use Newton's method, okay? But many times you do. The point is, at the end of the day, this is it. You're finding this. Now, likewise, if you want to find the bottom, you also know this. So this works top as well as the bottom. It doesn't work for this guy, okay? So you have to make some assumption. That's why it's the simplest case. This is what economists do. When economists build a model of how to set price, I want to get, they assume that there's some kind of maximum profit. Okay, maximum profit. Let me do this. You guys remember that price times quantity thing, right? Yeah, price times quantity. Let's say I set the price here. Okay. Okay. So price is not something that is variable, but you take for granted. You're actually able to set the price. You can set the price. Okay. Because after all, you're selling it, right? Let's say this is your profit. Now, if something is worth if you can sell something for 5 baht, right? Okay. And you make profit of 2 baht per unit. Okay. Right. And if this is forever true, what's the best decision you can make? Make as much as you can. Right? Make as much as you can. Right? Because people are always going to buy it. Conversely, you're already at a limit. You can only sell 1,000 units. Okay? If you are guaranteed that people will buy, well, why would you stop at setting the price at 5 baht? If you set it at 5 baht, you get 2 per unit. If you get it at 6, you get 3 per unit. Why not set it at infinity? Right? The point is you can't set it at infinity because people will stop buying. So this is the representation of that. If you set the price real low, you're not making a lot of money because it costs you something to make the stuff. To a certain level, you can increase the price and people will buy more of it. Okay, so they'll buy the same quantity at a higher price. So 1,000 unit at 5 baht becomes 1,000 unit at 6 baht. Maybe that works. You can get away with 7 baht, 8 baht. But once you get to 20 baht, you're not going to be able to sell that many. So by the time you take all this into consideration, the production costs, there's so many things in this. That's what economists do, right? In this case, microeconomists. At some point, you can have a function of total profit as a function of price you set. And because they know that it has a peak, set this equation, the price equal to 0, and you solve for this. That's what economists do a lot, okay? They do this for macroeconomic equation. They do this for all kinds of stuff. But life is hard. Life is hard. What do I mean by life is hard? Now, I want you to imagine, okay? Imagine. Remember that Newton thing? You only know where you're standing, right? You have to estimate where it hits the sea level, right? Likewise, I have another problem. You have this kind of thing that you want to maximize, except, well, let's make it simple. Except you don't have this function. Okay? You have this function, but you can't find this point. Let's say you're just standing here. So it's the same analogy, right? It's the exact same analogy as we had before. You only have what's called local information. Okay? You have local information. Here's my question. If you're standing here and I say, please go to the top of the mountain, what do? You walk. My question is, which direction? Right or left? Right. Yeah? Okay, fine. You're going to have exactly the same story. You're going to walk right. Let's say you walk right. Okay? That's your direction. You go to this step and you end up here. Okay? And where else you go? You go right again. Okay? And you take this step, you end up here. Now, what happened now? You realize that you evaluate your position again. Okay, let's say you don't have a good sense of balance. You only know your gradient if you take out the little measurement. Okay, so you stand here. Now you take the slope. The slope is here. So you actually overshot, right? So at some point you come over here. Okay, so this kind of thing, okay, it's like the Newton method problem I told you earlier where you only have local information. But here, you're not trying to find 0. You're trying to find the peak. Okay. Now, conversely, okay, most of the time, instead of talking about maximizing profit, I want to talk about minimizing costs. Same thing. Right? So you're not going to find zero in this case because your cost will not be zero. But you want to, once you start here, you want to keep going until you stop there. But it's not a one-shot thing, right? Economists can do that because you can solve global function and say, that's the best solution. Now, in this case, your life is hard. You can't get there at once. You have to iteratively find your way. This is gradual process, okay? Now, the notion here is that you're going down. So there's a word called descent. By the way, you can also do ascent, mean going up, but it's the same thing as putting a minus sign, okay? So most of the time, because energy minimization is a big deal in engineering, we're gonna talk about minimization, okay? So when I tell you this is the minimization problem, you can say, no, actually it's a maximization of the minus of that function. It's the same thing, okay? So by convention, we go with minimization. So it's called descent because you're going down. Now, the direction, any of you been Boy Scout? Okay, well, when you read a terrain map, right? You guys seen this, right? Right. Now, in one dimension, it's obvious, right or left. In high dimension, let's say this is your terrain map, okay? And you're standing here. Now, this is where you want to go, right? This is where you go. And I'll show you this. This is very important. Can you guys imagine this? Let me draw it again. Actually, let me go to empty page. Okay. Now, I'm assuming you can read contour map. Okay. Can you guys see this? This is called, this is the same height, okay? So this is higher than this, higher than this, higher than this. I want to go to the bottom of the valley, okay? Actually, you're standing here. Okay, actually you're standing here. If you were a helicopter, how would you do it? You just go there, right? Now, again, you're not allowed to do that. You're not allowed to do that. The name of the game is you only see where you are. Where you are, you know that you are higher than where you want to be. You also know that you can go lower, right? Now, the example where like this, it's right or left, but here it is what? 360 degree. So how would you go? Which direction would you go? Well, you would take out your little, what's called gradient meter. You know what a gradient meter is, right? It's like a ruler. You put down, it says 0 degree. You put it like this, it says 10 degree, right? So what you do is you take your gradient meter and you sort of like try 360 degree. This is an algorithm. You go to the direction that gives you the highest gradient. So maximum gradient. In this case, you would go here. Okay. Now, if you take a giant step, go there. Okay. That's not good. If you take a tiny step, it takes you a long time. So there's some kind of trick, some kind of art to it. But let's say you take a step that's of the right size. ให้ลบทีละนิดได้ไงไม่ได้เนาะ Anyway, that's okay. That's okay. Yeah. Okay. Good. Now I want to go back to writing and let's see. What I want to do is this. Take some kind of small step, right? Find out again. Take out my little gradient meter. Find out what the maximum gradient direction is. And I'll probably go here, go here, go here, go here, go here, go here. Right? This is a very clever algorithm. Okay? This is the gradient descent, maximum gradient descent. Okay? This is how you find the bottom. Okay? The bottom can be the minimum cost. Now, I'll tell you right now, this is like a foreshadow. This is kind of like spoiler. For, again, 40% of you are probably going to sign up for Applied Digital Intelligence. This is the heart of machine learning because the height corresponds to machine learning error. The height corresponds to machine error. So what you want to do is build a better machine learning model than your friend, right? So you want to minimize machine learning error. By the way, what's this? This here is 2-dimension, right? It's the value of location. Well, those value of location will correspond to what's called model parameter. Okay. The difference, and this is where life gets difficult. Here, how many parameters you have? 2. Horizontal, vertical, right? Horizontal, vertical. Well, in machine learning, this is an error you want to minimize, except instead of having x1 and x2 to find, you have x 100,000, let's say, or 50,000 or 5,000. So it's a bit more difficult. Okay, that's why you have, and again, you have the same situation where you don't know what the best is. You can only locally evaluate. So what in machine learning, again, even though you're not going to apply digital intelligence, you probably be using machine learning. What happened is wherever you are, you find out if you can tweak your machine learning parameter in the direction that would lower your error the fastest per step. So maximum gradient means for 10 centimeter in 360 degree around you, this centimeter will give you the biggest descent, the biggest drop per horizontal distance. That's what it's mean. Okay. So likewise, for tiny move in the parameter of your machine learning model, how fast you want to go to lower your error. That's what it is. Okay. So machine learning algorithm is all about doing this. Okay. So that's the power of calculus. Okay. Again, and I'll just show you. This is one side. Again, this is from Mathematica's demonstration. For example, this is a very nice depiction of the picture. Okay, the guy standing here, right? Obviously, by the way, the deepest gradient descent direction is the direction perpendicular to the contour line. You should know that from Boy Scout, right? So this is, if this is your you've been dropped somewhere. This is your Boy Scout map, right? The greatest descent is always perpendicular to the line of the contour line of the map. Okay, so the guy goes here, 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 here. Okay, that's what it means. Except again, right? This is a 3-dimensional world where you have one depth and you have 2 dimensions of location. Okay, in machine learning, the depth corresponds to error, and you don't have 2 things coordinate in 2 positions. You have coordinate in 3,000 parameters. Okay, so that's a little bit tricky. Okay, that's a bit tricky, but that's again, because now it's a generalization. It's a little bit beyond of what I told you, because what I told you is y is a function of x, just one x. In this case, y or error is a function of 2x already. So this is already multivariate calculus. So that's a little bit, okay. That's already a little bit beyond what I asked you to envision at first. Okay. So with that, I think we have to, oh yeah, we have another thing. We have to finish on time today. So that's good because we finished everything. So I'll see you on blah, blah, blah. After this, there is, you know, why do you have the integrated education? It's sort of orientation talk for the incoming class, except last year we didn't have this. So this is kind of open for previous class or whatnot. So you guys can, you know, sit where you are if you like, but because it's meant for you actually. But let's take 5 minutes break and we'll go to a different room.